All right, thank you all very much. Okay, so Dan just gave an excellent overview of some of the compositional questions that arise from SPA. You know, we're still left with the question of where did this stuff come from? If there was more time, and I'd take time from my talk to gladly ask Dan, what does it mean? Is it impact melt from SPA? Is it impact melt from these other basins or craters? What does it all mean? So one of the things I'm going to address today is not what does it all mean yet, but some further questions about where some of the material inside SPA came from. Let's go forward. All right. Slide. So if you get in your time machine and go back to Bill Bodke's talk yesterday, and this is really what sort of got me thinking about what is the record of some of the oldest basins remaining in SPA. So Bill presented a hypothesis about the giant impact ejecta reaccreting and forming basins, pre-Nectarian age basins on the moon, and that there may be a record of a very narrow window of bombardment, about 8 million years, immediately following the giant impact. And so the question that I sort of came up with after that, as well as any record of that remaining within SPA, if samples come back from SPA sometime in the near future, we hope, would we be able to determine some sort of early cratering flux early right after SPA formed? And so what I set out doing is that sort of addressing the question of what could we possibly sample from this very early impact cratering record immediately following the formation of SPA. So just to recap a couple of the previous thoughts that we've had on the regolith within SPA, and Larry Haskin set this out almost 10 years ago now, is where does the regolith in SPA come from? We know that there's obviously a very strong compositional anomaly there, so the regolith to some degree still records the ancient composition of the basin interior, but how diluted has it come over 4.5 billion years of impacts? And through Larry's modeling work and some work that Carly and I did, we concluded that the floor material in SPA, while it is slightly diluted by subsequent impacts, obviously still retains some of the ancient floor material in the regolith, in the prospect of about 50% or more. And that looking at sort of across the entire basin, that the 4.5 billion years of basin bombardment or bombardment after SPA, that in general a very small amount of material is introduced into the basin itself. And so these early works, I think, at least I know, I kind of treated ejecta from other basins as being kind of naughty stuff that we wanted to ignore or try to understand how much it is. And now what we try to do is, well, what's the good stuff that comes out of these small contributions from other basins? And in most recent work, and presented here at the forum back when it was an NLSI, we looked at how small craters are contributing to and modifying the regolith within SPA. Specifically, how much melt smaller craters are contributing to the regolith. And ultimately, through some modeling work that Barb has done and applied to this problem, we find that small craters, while they are remelting some small amount of material and injecting it, aren't really diluting the regolith with this naughty post-SPA melt material into the regolith. So, with that said, let's look at what's happening right after the formation of SPA. And so Caleb Fassett a couple years back looked at a number of basins and started using LOLA data, put them into a revised stratigraphic sequence. And so what I did is took that list, looked at just the pre-Nectarian age basins in or immediately around SPA. There's 5 that we consider for this work here, including Australia, which is somewhat anomalous. And Bill talked a bit about that yesterday, located just to the west of SPA, and 4 basins that are in or right on the rim of the basin itself. And of course, each of these subsequent 5 basins are in somewhat unique environments. In the past, we've talked a bit about the Poincaré and Apollo basins, which have some of the thinnest crust on the moon beneath them. Of course, Ingenii Basin, which is near the thorium enhancement within SPA, and the ancient Amundsen-Ganswit Basin, which has been cut by the Schrodinger Basin as well. And of course, there's other pre-Nectarian age basins across the moon. We only are looking at the ones within SPA right now. So we really ask 3 questions. How much melt is created and distributed by these impact events? How much of their ejecta and melt is deposited into and remains in the regolith today? And what's the variability of this across the interior of the basin? And so with those questions, we set up our examination. Dan talked a lot about the interior of the basin. I don't need to get into this too much. Did want to build on what Ben talked about with the diviner work and show some of the variability in the Castrantian feature across the basin. Of course, as Dan mentioned, there are the mafic areas across the basin. There are also some areas that are surprisingly plagioclase rich, so we don't have much in the way of mafics across the floor. An important aspect of what we do here also is considering that there's volcanic activity that have taken place within the basin, and Jenny talked a bit about that earlier on as well. And so, of course, the regolith record in those areas is completely different. So we're going to put that off to the side today. So the three basins that we consider inside of SPA are marked here, and we'll talk a bit more about that in a moment. So the first thing I want to talk about is this a parameter, the fraction of melt that Barb developed, which is how much melt material is present in a crater's ejecta deposit. This is the result of the calculation of the volume of melt multiplied by the efficiency of melt ejection from the crater. And so this is, the model assumes that this value is relatively invariant. So for these basins, the 5 basins, and I include Imbrium because it turns out, as we all understand, Imbrium is a very important player, not just on the near side, but potentially even on the far side as well. So these values we'll see time and time again, but essentially what we're saying here is that in the ejecta deposits from these basins, this is the fraction of melt that's in those ejecta deposits. So just to begin with, they're relatively small amounts of ejecta. So, sampling ejecta from Poincaré or Adamson-Gantzweit, it's going to be a small amount of any ejecta deposit. Obviously, with subsequent impact cratering and gardening, those materials are going to become diluted, so it's up to us to find out where some of the ideal places to go potentially would be to get these samples. So ask the question then, if this material is in the ejecta, what is the distribution of ejecta from just these basins? So let's go to that slide here. Now this follows on the modeling work that I've done in the past. I use now the Facet et al. Ejecta scaling model. Of course, we make several simplifying assumptions, uniform distribution of ejecta outside the basins. We don't take any asymmetries into account. We can sort of assume that it's uniform. Obviously, there's going to be clumping and clustering. This is not going to be continuous, but for the most part, especially for these 3 basins, the ejecta is, we're talking about fairly close into the basins, and so we haven't quite gotten into the very distal material just yet. Off of the figure here, outside of the main area we're looking at are Austral and Adamson-Gantzweit, and that's those 2 basins in particular, Australia, are what are causing this enhancement in the southwest of the figure here. Let's change the stretch a little bit so we can see some of the underlying topography or geology, and also identify 3 places that we look at in a little bit more detail. Previously, we identified this sort of straddle point between Poincaré and Apollo as being unique because of the thin crust beneath those basins. So we're going to look at this area in a little bit more detail. This is near Bose and Baba crater that Dan mentioned a little bit before. Look to the southwest of Ingenii and to the west of Poincaré to assess what's in the regolith there from these basins. Okay. So just in general, first thinking about the ejecta distribution, of course, Australia is a big, weird basin. And as such, and because of its large transient cavity size, it's going to be the main contributor to the ejecta in this area across the sites. The variations from other basins are strongly site dependent. So obviously, the further you get, say, from Apollo, from site 1 to 2 or 3, the amount of Apollo ejecta decreases significantly. Remember, we have a negative power law describing the decay of ejecta from these basins. And so the other part of it is thinking, well, these are all very early basins. You've got several large basins that form everywhere else on the moon, impact cratering. How do these deposits survive, and how well do they get diluted? One of the surprising things, perhaps, coming out of some of these regolith mixing models is that while a basin might contribute a little bit of material that's coating the top, it gets very quickly diluted by subsequent mixing. It's like sprinkling the salt on top of your baking. Eventually, once you add the egg and everything else, it just gets disappeared, even though it might have coated the surface initially. And in what proportion do these materials survive today? So let's look at the first site, and this is this location southwest of Bose, sort of in the center of the basin. Again, we have the fraction of melt from the basins that we talked about before, and I include some of the larger, more recent basins, just as a basis of comparison. We've got, obviously, Imbrium, as I said, is a major contributor across the whole moon. The Oriental Basin, which is relatively close to SPA, and of course the very young Schrodinger Basin as well, also within SPA. And include one of the more recent smaller craters. Of course, we'd like to know where it falls within the sequence of events to better place it in the mixing. So the middle column there is the fraction of ejecta at time 0. So that's immediately after the cratering event. How much of the ejecta from that particular event is at the surface? And so that is a snapshot in time that does not survive to the final column, fraction ejecta at time now, or roughly now anyway. And what you can see is that for most part, most of the basins don't survive. The material gets diluted into the regolith with mixing. Basically what that's telling us, and actually if I go to the next slide, I sort of describe it in some more detail. That material is, again, that salt coating the surface that just gets diluted into the regolith very rapidly with subsequent events. Big events, Serenitatis, Imbrium, at least through this model, are the ones that are diluting the regolith across the whole moon. This is very dependent on the order of basins. Because we're specifically focusing on very, very old basins, it shouldn't be a surprise that these materials get diluted. However, this time now, and I describe it as being the worst case scenarios. I'm not sure worst case, it describes a little bit too much of a concern. These are certainly the most, the most destructive cases. And so this is likely a lower limit, and so hopefully it doesn't scare anyway from the thought that perhaps some of this material actually is surviving in the regolith. However, I do want to remind you that the fraction of melt in these ejecta deposits is incredibly small. So we're not talking about a large proportion of material going out. Southwest of Ingenii, too, not surprising. The material is much different than what was in the center of the basin. Larger contribution from Australia, and again, most of the material from other basins does not survive to today. And last step to Poincaré. Australia, again, is now beginning to dominate the regolith. One of the things from all of these modeling efforts we see is that really, if you're close to a big basin like Imbrium, Apollo 16 at Imbrium, or this site next to Australia, that regolith is going to be dominated by its ejecta, and so we'll see strong signatures from there. So we've seen that there's a variability across the basin, across the floor of SPA, in what survives and what's available to be sampled today. So let me end with some concluding slides. So we have modest contributions from pre-Nectarian age basins across SPA. It's there. It's probably in very, very small quantities. Of course, the difficulty is if they are all forming within a very narrow window of time, pulling out each event might be somewhat tricky, but I'm convinced that Barb can do it. Maybe she doesn't believe it, but I think she can. Any of the three sites, however, are going to still be dominated by the SPA floor material. That will survive. It does not become diluted. Ultimately, we're talking about 78% or more of the regolith in these locations are going to be either pre-Nectarian basin or SPA floor material. And of course, we all know that the laundry list of reasons why a sample from SPA would be good. And it seems like every year we add more and more and more on top of that, but there are a lot of good reasons to go get samples from the floor of SPA. With that, take questions. Thank you.